So welcome back to Computer Science 4303. Today we'll be going over Assignment 5, so what you have to do for Assignment 5, as well as a talk about StarCraft AI research. So far, we know that in the course, your project, one of the topics for the project is to write a StarCraft AI bot. So in the past couple of years, in the past couple of lectures, feels like a couple of years this term though, we've gone over the setup for the StarCraft stuff. We've gone to how to run an AI bot, what the AI bot is all about. I went over a whole lecture of an intro to StarCraft AI programming, how you interact with the API, etc., etc. And today I want to jump ahead into some more advanced stuff. Now, this isn't necessarily like, we don't have an exam on the course. You're not going to have to implement this stuff on your project. But what I wanted you to do is to get a feel for the type of research that at least I've been doing in the field of StarCraft AI and why that is an important field of study. So we'll talk about Assignment 5 a little bit, and then I want to do the rest of the lecture on StarCraft AI research and some of the important topics. And if you are interested in any of these topics, these are topics that you could potentially work on in graduate school or something like that if you really want to. So yeah, let's just get into that now. Let me bring up the PowerPoint view. And here we go. This is actually lecture 17. Let me change that. Boom. All right. So as I said, we're going to be talking about StarCraft AI research, but first, I'm going to talk a little bit about Assignment 5 here. So Assignment 5 is going to be first a project. So there's two parts to Assignment 5, and it's going to have two due dates. So it's going to be actually Assignment 5 is going to be split up on D2L into like project proposal and Assignment 5. But essentially, it's two things for the price of one, right? So the first thing is this project proposal. So I want you to write a page on what your plan is for the actual project. So now that you've gotten a taste of the API and you've set it up and you've written a little bit of code, I want you and your group members to sit down and say, okay, what is it that I will actually be doing for the project? And within that, what specific AI features are you going to focus on in the project? So here are some due dates. So March 19th is going to be, and that's on Friday. So this is Tuesday, if you're watching this later. This is Tuesday, the 16th, and this is due 3.5 days from now. Okay, so midnight on Friday is when I want this due. And I want you to work on this really quickly because I don't want this to bog down progress for the rest of the project. So this Assignment 5 is really just some kicks in the bum to make sure that you are working on the project. And I think once you get this taste of working on StarCraft AI, and not only StarCraft AI, but also the Minecraft project, once you get like a taste of working on it, you are going to really enjoy working on it, I think, and continue to work on it and not leave it until the last minute. So the way the rest of the course is going to go, I said this a couple of lectures ago, is that the remainder of the work that you'll be doing is going to be on the project. Okay, I'm going to have some additional lectures in the future on other AI topics that will be, hopefully useful for you in learning about AI and possibly techniques that you could use in your project. But I really want to hammer home that, we're going to be working on the project pretty heavily from now until the end of the course. So on Friday, I want this one-page proposal, and I will talk a little bit when I get to a specific part of this lecture about if you're doing StarCraft, what I want you to work on. And if you're doing Minecraft, what I want you to do is to this sort of what specific feature will you focus on for Minecraft. Excuse me. So for Minecraft, what specific features will you focus on? Let me do this last point first, is that full painstaking details will be released in a D2L post tonight. Okay, so take today to work on the Assignment 4, which is due tonight, and then I will have the details up at some point this evening, all of these details specific to each project. but it's a project proposal. So for example, one thing you could do, let's say you were doing a StarCraft project, right? So you could say, our plan for the StarCraft project is that we are going to write a bot from scratch using the starter bot. And that bot will play it will focus on a two hatchery Hydralisk build for the Zerg. Okay, and what our goal would be to be able to defeat the default AI that comes with StarCraft some of the time using a Hydralisk build with the Zerg race. Okay, and in that, what specific features will you focus on? Well, we're going to have to focus a lot on being able to upgrade our Hydralisks and work that into our build order somehow. Or Hydralisks can burrow and unburrow, and we would like to be able to effectively use the burrowing skill in order to help us with micromanagement in the project. Something like that, right? So it doesn't have to be like a grand scheme, right? It's just, okay, you can focus on one of the 3 StarCraft races, and you can focus on one specific strategy that you want to implement, right? This is not a StarCraft AI competition. You don't have to be able to like stop all sorts of attacks and all this sort of thing. You are just focusing on one thing, because the idea here for the project is that you get a flavor or a taste for what programming AI in industry would be like, right? And programming AI in industry is dealing with all these nitty-gritty edge cases that StarCraft can throw up. How do I build buildings? Where am I going to build them? When would I attack? How would I attack? How do I control my attacking creatures? So that's what your project is going to be. And then on March 30th, so 2 weeks from today, you're going to be submitting some sort of proof of progress, okay? So this is what we have so far. So far, we are able to get to the point where we are building the Hydralisks, right? Or we have built the Spire and a Mutalisk comes out. Or we've gotten a siege tank produced. Or we are able to effectively scout our opponent and harass their workers, or something like that, right? So that is what, and I will include in the D2L post a bunch of examples of project proposals and a bunch of examples of specific features. Now, for the Minecraft stuff, what I would like you to say here is something like, we plan on making a settlement that is very heavily focused on like the lore or something like that. So we're going to have really detailed interiors. We're going to have like villagers you can interact with. You can place those in the town. Actually, I'm not sure if you can have villagers. This is just an example. Or you could say, our project is going to be focused on building tree houses, right? Like if there are trees in our environment, we're going to build tree houses that interact with the trees and look really cool, right? Some of the specific features you can focus on for the Minecraft thing would be, for example, if you make a town and you want there to be roads connecting all the buildings in the town, right? You might have to use some pathfinding that we did in this course in order to be able to say, okay, we want the paths between the buildings to be really efficient. And so we're going to have to do some sort of shortest path or something like that inside the project. So the details of that will be there, but this is the timeline we're sort of working at, okay? Is that by Friday, I just want this really simple one-page proposal. Doesn't even have to be a page if you've explained it all correctly. And then 2 weeks from now is going to be the proof of progress that you've actually continued to work on this project and you're not leaving it all until the last minute. So that's what the assignment 5 is going to be about. And I'm going to release a post on D2L tonight that you can check. That's going to have all of those details for you. Okay, so that's assignment 5. There's some people asking some very specific questions about BW API and stuff. If you're in the course, ask those on D2L, and I'll get to them later. I'm not going to be answering those very specific questions that aren't, about the lecture during class time. Okay, so the rest of the lecture is going to be, I want to talk to you about some of the cool stuff that I've been working on throughout my research career. And there are way more people doing all sorts of cool stuff in this, but I'm an expert on what I've done, so I want to tell you like why that might be interesting. So some sort of motivation and introduction for StarCraft AI research, which is at the graduate school level. So if you go on to do a master's or a PhD, My PhD was in StarCraft, which was really lucky that I was able to do that and really cool. But I want to tell you why, that's actually interesting. And, we're not just playing video games for the sake of it. It's actually interesting research. First off, I want to remind you of Computer Science 3200, right? So Computer Science 3200, which is a prereq for this course, in that course, we talked about game environment properties. So if any of you out there actually remember this stuff, environments have properties such as they can be episodic or sequential, they can have single or multi-agents, they can be deterministic or stochastic, they can be fully or partially observable, they can be static or dynamic, they can be discrete, or continuous, right? And so if you look at this sort of hierarchy that we went through in terms of kind of determining how hard a problem would be for AI to solve, we use these ever increasingly difficult properties in order to help describe how hard a game might be. So for example, we have a crossword puzzle. Well, a crossword puzzle is going to be sequential, but it's single agent, right? It's just a puzzle. You're the only one playing. It's deterministic, it's fully observable, it's static, and it's discrete. If we then add multiple agents, we get a game like chess, right? Where now you have two players playing against each other. If we want to add in some randomness, now we have something like backgammon, where you have like a roll of the dice. If you add in partial observability, then you get a game like poker, where you can't see the cards of your opponent. But then if you add in a dynamic aspect, right? And dynamic versus static here means that if something is static, then it just waits for you to make a decision, versus a dynamic environment is constantly moving along until you make a decision. Right? So in StarCraft, it's completely dynamic. If you take too long to make a decision, well, your opponent is just going to kill you while you're waiting, right? So it makes the game much, much harder. So StarCraft as an environment is probably the closest environment we have to the real world in terms of video games, right? Because it shares all of these properties. Except whether or not you want to believe like the universe is discrete or continuous, it's arguable that the real world is a harder problem to solve than StarCraft. Okay. So some of the properties of real-time strategy games that we just talked about, again, it's real-time. You have simultaneous moves, so you and your opponent are actually acting at the same time, which is an additional problem. So unlike chess, where you get to see a move and then respond to it, you're acting at the same time. It's non-deterministic. There is some randomness in StarCraft with respect to like unit targeting and where you get placed on the map, etc. It's imperfect information, so you can't see your opponent units unless you scout them. You don't know how many resources they have necessarily. You've got multi-unit control, so you've got this sort of exponential action space that you have to worry about. You have an unknown game engine, right? So you don't know the game engine, so you don't have the source code, so you've got to make some guesses at some sort of things that are happening inside StarCraft. And you've got this action and state space, which are just gigantic. And let me go into that just for a little bit. So what do I mean by the state space? So the state space for a problem is basically the number of configurations that the game could possibly be in, right? So if you think about a game like tic-tac-toe, right, where you've got 9 spaces, or X's and O's or noughts and crosses, depending on what country you're from. You've got 9 spaces. Each of those spaces can have one of 3 different entries. They can either be blank, they can be an X, or they can be an O. And so in that case, you've got maybe a few hundred different possible X and O boards that you could possibly have. If you move then up to a game like chess, right, you've got a bunch of different pieces that could all be on different parts of the board, and you've got a state space for chess that's like 10 to the power of 140 or something crazy. It's just like a gigantic state space. But StarCraft blows every other game out of the water in terms of its state space size. So typically what you have, if you look at the build tile level, so we're not even talking about the pixel level here. If all you do is look at the build tile level, which, you know, an average map might be 128 by 128 in size, you've got up to 200 units, and you've got 50 different unit types, just the combinations, the possible combinations for unit locations on the map is 10 to the power of 1685. Okay? So if every atom in the universe contained a universe in which every atom was a supercomputer, it wouldn't even come close to being able to enumerate all of the states of the game, right? Now, that's not to say that every possible state of StarCraft is interesting or that every possible state of StarCraft has to be explored. It just means that the game is so large that we can't apply like breadth first search and just hope to solve StarCraft, right? We've got to come up with something a lot more interesting in order to help us deal with that sort of state space size. All right, so we talked about these properties of real-time strategy games, right? Well, these are also the properties of robotics, right? If you think of robotics, they have to deal with all these problems as well. And they're also the properties of the real world, right? So the idea here is that we are using StarCraft as an environment to test AI systems that could then be also applied to problems in the real world or problems in things like robotics or other, more important fields of research. But what could actually be more important than video games? Well, it turns out that even if all you do is care about video games, it's still an important problem to work on, at least economically. Like here, these are figures from just 2018, and these figures have ballooned since then, right? So video games are worth hundreds of billions of dollars per year globally. And so it's an important problem to work on because industrially and economically, this is an important part of society. Like music and movies often get like this reputation for being art or for being important economically or socially. But music and movies combined do not match the economic scale of modern day video games. Like video games sales are more than that of movies and music combined. It's kind of crazy, but like they are just as much an art, they are more of a science. And someone out there saying preach. Yeah, I do sound like I'm preaching. But what I'm trying to say is, even if all your research does is get applied to video games, that's still an important problem, in my opinion. Like, not all of us have to be working on cancer research, right? Like, that's often like viewed as, oh, as long curing cancer, that's what we want to spend our money on. But there's lots of other important problems as well. So some benefits of RTS AI in the video game space is that, well, first of all, you're going to create better in-game AI, hopefully. So you're going to have better, more intelligent NPCs, and those more intelligent NPCs, hopefully, are going to provide for a better single-player experience, right? For example, whoever solves the problem of making good escort missions in MMORPGs is going to make $1 billion, right? So let's do some great AI research on escort missions to make them not suck. That would be great. Alrighty. Also, something that I'm focusing on more now is that when people think about AI in video games, they think about basically only what moves a character around the screen, or the AI that's controlling something that's doing decision making in real time in the game. But that's not the only application of AI in video games. Something that my research is pivoting to more nowadays is actually in the creation of offline tools for video games. So if you have a really good AI for the game, not only can it control in-game NPCs, but let's say, for example, you had a really good StarCraft AI. Well, you could use that AI to sort of play against itself in order to see whether or not the game was balanced, right? So maybe you find out that this unit is always made by the AI, and so that unit might be overpowered, right? So you might have to tune that unit back, or that this unit is never bought for some reason by the AI system. So maybe we need to tune that one up a little bit. So creating offline tools can help reduce human testing a ton. Like, I can envision a future where there is very little human input in the QA process for modern video games, at least in the terms of like balancing or like bug finding, right? So think of an AI system that you create that's able to, let's say like you find a bug in the game where you can clip out of bounds, right? That is what human QA is doing now. Like, the companies literally pay dozens of people to sit and jump into a wall for hours in order to try and clip out of it. But you can easily make an AI system that can figure out how to get out of bounds in a game, right? So why aren't they doing it? Well, because the research isn't there yet. And hopefully we can apply this to like any game, because, we can apply it to any game, because if RTS AI games are, if RTS games are so difficult to make AI for, then hopefully the solutions we come up for RTS games are going to be able to be applied to any game, because, you know, they're not as hard to play. Also, we have esports, right? So not only esports, but if you remember the AlphaGo movie that we watched in 3200, what happened there, if you're not familiar with AlphaGo? So AlphaGo is this superhuman AI system for playing the board game of Go. And it was really interesting, actually, because the humans thought that there was no way that an AI system was going to beat them at the game of Go. And so there was sort of this, like, you know, the 5 stages of grief, where it's like denial and then like anger, acceptance, like all that kind of like all of that went through human Go players throughout like the match with AlphaGo. And it started out, there's no way they're going to beat us. And then after they won the first match, it was like, okay, maybe they got lucky or the human was nervous. And then like 4 games in, it was like, okay, wow, this is pretty good. And by the end of it, they were like, the AI is so good that it's going to teach humans new ways of playing this game. And so that was really kind of fascinating to see go through that process of like not trusting that the AI was going to be good. And then at the end, we realized that having good AI systems makes us better at the game as humans, right? And I think this can happen in a lot of professional esports as well. Like if you have superhuman opponents to train against, then that means that you're just going to get better by training against them. Training against people who are better than you makes you a better player. And so we have human professionals who play StarCraft and RTS games at an extremely high level, and they like 300 to 500 APM or even more in some cases. And so one of the really cool things about StarCraft AI research is that unlike a lot of other forms of research where like only AI experts are really able to identify like whether or not it's a good system, if we make a really good StarCraft AI, we've got hundreds of thousands of people out there who can actually evaluate our system and play against it and have fun and give us feedback. So humans are playing StarCraft, and it's great because they can give us feedback and tell us how good we're doing or not. Also, one of the ways that we have traditionally evaluated AI systems is by playing games, right? So there's this question in AI research of like, how do you actually do AI research? Like, what is the evaluation method? How do you know that one system is smarter than another system? How do you know that one algorithm is better than another algorithm in terms of intelligence? Well, that's a really hard question to answer. And so one of the solutions that researchers have been using, especially in the field of game AI, is let's take our new algorithm and apply it to a game. And if they beat the existing algorithms in that game, then it must be better. It must be more intelligent, because games are measures of intelligence. Well, at least traditional board games. And so, you know, when I made this slide years ago, we weren't even close to human play with StarCraft. But AlphaStar, of course, has gotten close to it's able to beat human professionals, but not the world's best, right? So we still don't quite have a check mark here, because AI systems for StarCraft have not yet beaten the world champions in any sort of official match, at least, for StarCraft. Okay. And also, it's fun to beat humans, right? You get a lot of press, you might get some funding, it's just fun to beat humans. So, now you're saying, okay, well, if StarCraft is such a hard problem, how do you even begin to tackle it as a research issue? And this part of the talk is also applicable to your project, because in the next slide, I'm going to show you some of the parts that you can actually focus on for your project. So if StarCraft is so big, how do we approach it? Well, what we're going to do is we're going to split the game into different subproblems. Okay, so we're not just going to try and solve StarCraft. What researchers have traditionally done is they break down the game into different strategic components that humans have used for years in order to try and play the game. Okay, so for example, and this diagram, I made this for my PhD thesis years ago, but it sort of shows all the different problems that you have to solve in a StarCraft AI system. And not only that, but like categorizes those problems into sort of the time scale at which they occur in the game. Now, you may also say, okay, but AlphaStar didn't do any of this, right? Yes, but AlphaStar, it applied reinforcement learning to the game sort of as a whole, but it did have underlying features inside the... How do I explain this? The AlphaStar system learned the game as a whole, but the features that humans handcrafted for AlphaStar in order to learn took these strategic elements into account, okay? So when AlphaStar was learning, it used features, visual features, and those features were hand-constructed by humans to have strategic importance in the game. So even though you may want to apply machine learning to all of this, this is still an important breakdown. So that's just a little aside about machine learning and people's criticism of this sort of method of research. So before AlphaStar, right, this is how we break down research in StarCraft. So first, let me show you what a typical game of StarCraft looks like from a human point of view and how these categories fall into that. So when you start a game of StarCraft, first, what's going to happen is you're going to start the game with some amount of knowledge, right? So maybe that knowledge includes, well, I know the prices of all the units. Maybe I know how much damage they do. I might know what the map looks like that I'm playing on. Maybe I know that my opponent... I'm not going to get into that yet. Maybe I know... maybe the build order that I'm going to do in this game, right? So you're going to start off the game with some amount of knowledge about the game and about the environment. Then, you're obviously going to be playing against an opponent. So you're going to be doing some sort of opponent modeling, right? So you might know absolutely nothing about your opponent at the start of the game. Or maybe you're in a human tournament and I'm playing against Jaedong, right? So I know that they're going to play Zerg. I know that they're way better than me. I know that they're going to use Mutalisks and destroy me with it. So maybe I should make some anti-Mutalisk things, right? So based on the knowledge that I have of the game, I'm going to use that knowledge to model my opponent somehow. You don't have to have a model of your opponent, but you can. And then based on that knowledge and that opponent, I'm going to take some sort of strategic stance within the game. And what that means is, okay, based on my knowledge of the game and based on maybe I think the opponent is going to rush me, right? I'm going to take a defensive stance within the game. So I'm going to defend this game because I know that they're going to rush me. I could be wrong, but that's the stance that I've chosen to take this game. Based on that stance, now I have to choose an army composition which is going to allow me to carry out that stance, right? So if I've chosen to play Terran and I've chosen to be defensive, maybe I need to build some tanks, some turrets, and some bunkers, right? I need to build those defensive units. That's going to be my army composition this game. So, now that I have my army composition, I need to figure out how to build that army, right? I can't just magically produce these tanks. I have to take a sequence of economic actions, and that's a build order. So I've got to plan my build order somehow to get the army composition, to get the defensive strategy that I'm going to use to play against my opponent. Also, I'm going to have to position these units somehow in order to do battle with my opponent. So once I've gotten my build order, right, then I'm going to have to actually do battle with my opponent. So I'm going to figure out when am I going to attack? When am I going to defend? I've also got to figure out where am I going to place these bunkers, these turrets? Where am I going to place these buildings, right? In order to actually carry out the attack, carry out the building placement, I have to be able to micro my units. I have to be able to move them around the map. and I have to be able to do some sort of pathfinding, right? In order to say, okay, if I place my units here, then I won't be able to leave my base, or I won't be able to attack my opponent so fast. So this is this sort of this hierarchical approach to the knowledge representation and the stance that you take in a game of StarCraft. Now, we don't typically think of it in this way when we're playing the game, but this is how your knowledge gets passed down from one strategic point of the game to another. And all this time, you are scouting, right? So you're sending out units, you're scouting the opponent, you're getting new information, and if you're scouting, if your information changes, that gets passed back into your knowledge and your opponent model. And your knowledge informs your scouting, and your scouting informs your knowledge. And if you figure out, oh crap, they're not going to attack, they're going for an expansion, well then I've got to change my strategic stance to maybe be more aggressive. And so this is a cyclical process, right? Throughout the game, you are gathering information that informs your knowledge and your opponent model, which is going to change your strategic stance, which is going to change your army composition, which is going to change your build order. So it's a really complex type of game that you're playing. Up here, I've labeled these sort of things. So these are what I would call strategic decisions. They are high-level, abstract problems which take place over a long period of gameplay. So for example, your strategic stance, I'm going to be defensive. That's a stance that you're going to take for some period of time in the game and carry it out and see how it goes. The sort of tactical or mid-level problems are things like scouting, combat timing and positioning, unit and building placement. So for example, a strategic decision is I'm going to be aggressive. A tactical decision is I'm going to flank them. A reactive control decision is going to be how I individually issue commands to each unit in order to carry out my tactical goal. Okay? So that's what this is. And for the assignment, what you can do is you can choose one of these areas that you want to focus on. If you want to focus on the build order planning, if you want to focus on the army composition, if you want to focus on the unit micro, that's fine. If one of these things really appeals to you as a group that you want to work on, this is one way that you can help make your decision about what you want to do. And my particular research that I focused on for my PhD, and I continue to focus on, are on the areas of build order planning and unit micromanagement. Okay, so I'm going to go over a few of those and talk about like what the problems were, what we did, in order to just give you like a little taste of what StarCraft research could be, if you ever did want to do that for, say, your master's degree or any other academic pursuit. Okay, so first is build order planning and optimization. I have explained what a build order is in this course already, so I don't need to go over that definition. But essentially, what I did for my research was write a build order planning system. And so what it did was, given a goal set of units that you would want to construct, right? So for example, I want 4 Marines, I want 12 Mutalisks, I want 3 tanks, something like that. And a current game state, which means, like, for example, if you're at the start of the game and you want 12 Marines, my code or my research, it was a build order search algorithm, which when it ran the search algorithm, and we did search algorithms in 3200, it produced a build order sequence that got us to that unit goal in a time optimal fashion. So what I wanted was, if your bot could somehow tell you, I want 3 siege tanks, then my build order system would look at the current state of the game, and it would do some sort of search algorithm, and then it would come out with a build order sequence that got you to that build order. And I'm going to describe a bit of that system. However, first of all, you need a simulator, right? So we don't have access to the StarCraft source code. So recall back to when we did things like depth first search and breadth first search, okay? When you're doing those sort of search algorithms, you need the ability to like copy a state. You need the ability to issue actions. You need the ability to like backtrack or fast forward, right, in your simulation. And And we can't do that with StarCraft because we can play a game forward, but we can't go backwards. We can't save and load states really easily. And so what I had to do was write my own build order simulator. And I called this BOSS. I always try and come up with clever acronyms. So it was the build order search system. The build order search system, which is not specific to StarCraft. The search algorithms would work for any games, but the simulator was specific to StarCraft. And so what this was is, let's say we take the full engine of StarCraft, right? So this has like all the attacking, it has all the animations, it had like the loading of the maps, all that kind of stuff. And we take that and we strip it right down to just give us enough computation to compute build orders, okay? So I want to show you something real quick because it's something that I've been working on for my research very recently. So I'm going to load this up. Okay, so let me go back to my middle monitor. So I sent this link out on Discord, but essentially this is a front-end user interface to, and let me get rid of all this stuff. It's a front-end user interface to my build order search system. So I've just posted in the chat. If you want to play along with this while I'm doing it, that's fine. So what happens here? Well, I'll explain a little bit of the interface to you because I like, everyone wants to show off their research. So for each of these columns here, we've got a starting state and a build order. So the starting state of StarCraft, you start with 4 workers. So you can see here you have 4 probes and you have a nexus and you have 50 minerals and 0 gas. That's how you start every game of StarCraft. So what this does, this system doesn't do the search yet. I'm still building that part of the user interface. But what it will do is allow us to visualize build orders. So let's make a little build order here. So what I'm going to do is I'm going to click on probe because I want to put some probes. The first thing we're going to do in most of our build orders is we're going to make 4 workers. Then we're going to build a pylon. Then we're going to do like maybe 3 more workers. And then we'll build a gateway and then another probe and then a gateway. Where is the gateway? And then maybe we'll build a pylon and another worker and another worker, and then we'll build some zealots, okay? So zealots, and then another pylon, and then some more zealots. So if I want to see what that build order looks like, I can click Draw Build Order, and it will draw it right here. So let's just zoom in on this a little bit. So this is the simulator that I wrote that actually gathers minerals, it gathers gas, it builds buildings, it produces buildings. And so what you get out in the end here is a visualization of that build order. And you can see here that going from left to right, I don't have it finished yet, and I don't have the exact seconds or the tick marks on the x-axis yet. But this will show us how long it takes to build those units. And it also shows us the parallelism in the build order, right? So for example, right here at this point in time, you can see that there's a gateway constructing, there's another gateway, there's a pylon, there's a probe, etc. So the cool thing about this is that if I want to compare if one build order is better than another build order, I can do something like the following. So I can select everything from this build order and I can copy it over to another build order. And then I can select everything from this starting state and copy it over. Now let's say what would happen if I built my gateways earlier. So I've just moved my gateways up in the build order. So if we look, now what I have is I still have the same start. So I have 4 probes, pylon, pylon, but here I've built my gateways sooner than over here. So what I can do is draw the build orders, and then we can see that, oh, okay, well, what I've done is my zealots are going to be constructed at the exact same time. But look in here, there's a gap between the finishing of the gateway and the construction of the zealots. So if my goal is to get 6 zealots as fast as possible, well, what I can come do now is let's actually edit out some of this stuff here. So maybe I don't need these probes, so I can remove them. So let's just remove those probes and see now what's going to happen. Oh, look at that. So I spent a bunch of time making extra workers instead of really quickly starting building these zealots. And so what this does, the simulator allows you to visualize these build orders and say, okay, this is a way faster rush than the initial build order that I thought of. So it's a useful tool, I think. And once I get the user interface up and running here, you'll actually be able to put in a search goal saying, I want 6 zealots, and then it will do the search and it will show you what the fastest possible build order to 6 zealots actually is. Okay. So that's, that's just a little taste of the stuff that I do for my research, and I think it's really fun. Someone said, is there plans to have this also include timing based on unit creation time and estimated resource generation, or would that be a separate system? So no, so this literally takes into account all the workers you have, how much resources they gather. So if you have more or less workers, they will gather more or less resources. And, let me just actually reload this. So here I have the default is I have a Dark Templar Rush, Battlecruiser build, and Mutalisk build. So if I draw these, now you can see, wow, this is actually pretty big, how this works. So you see here that we can see that our Dark Templar build order is pretty time optimal, right? What I mean by time optimal is that in order to get to Dark Templars, we need to have a Templar Archives. In order to have a Templar Archives, we need a Citadel of Adun. In order to have that, we need a Cybernetics Core. In order to have that, we have a Gateway. So if you have a build order in which to get to Dark Templar, you're going to need to at least construct these 4 buildings in sequence to get to Dark Templars. And you can see here that this build order only wastes like a few seconds before the construction of the first gateway. And the reason it wastes this amount of time is because it doesn't have the resources yet, right? So whenever you see a gap in the build order, it's because either the building required to construct the thing wasn't ready yet, or the resources weren't ready yet. So you can see here that there's 2 Dark Templars building at the same time. Well, why wasn't there a 3rd building at the same time? Well, the reason is because there were only 2 gateways, right? So down here, for example, we have 2 battle cruisers. So you can see that the first battle cruiser started building right away, but the second battle cruiser had to wait. I think it was probably for the gas, right? So this is a very heavy gas build. And so this time waiting here, we probably didn't have the gas yet. And not only that, but if I move my my system here, my camera, you can see down here in the Mutalisk build that it was waiting for this spire to be finished, right, before it built the Mutalisks. But this also simulates the larva production. And so what we do in a Zerg build is that we stop the production of all units before we want to pop out like 12 Mutalisks at once so that we can overwhelm and surprise our opponent. So here what we're going to do is we're going to stop the production of other units so that we can let our larva build up, so that once we get the spire built, we actually can construct all the Mutalisks at once. So this does simulate everything about build orders. However, now I don't want to go into too much detail about this, but one of the abstractions, one of the things that it does do is in the actual game, someone asked about tactics. Literally all this does is give you build orders. So tactics, you got to figure out on your own, right? How did you figure out you wanted 2 battle cruisers? I don't know. What this system solves is you've given me a number of units. Here's the way to get them as fast as possible. Okay? So what was I trying to say? I was going to say something before that. Oh yeah. So like one of the things that it simulate, it doesn't do exactly how the game does, is in the actual game, your worker will travel to the minerals, and then it will gather minerals for a specific amount of time, and then it will walk back to the resource depot with those minerals, right? So you're going to have 0 minerals until it's done that whole thing, and then all of a sudden you're going to have 8 minerals, right? So maybe there's like 15 seconds or let's say it's 16 seconds. It might be less time than that. But in order to gather 8 minerals, it takes 16 seconds. In the actual game, you will have 0 minerals up until the point where the harvesting is done, and it will get 16 minerals. In my system, in order to make it way faster to compute, what it does is that every frame of the game, I calculated empirically the average number of minerals per worker per frame, and that gets updated every frame. Okay? So instead of just saying 0, 0, 0, 0, 0, 16, you're actually gaining like fractions of a mineral every frame per worker. But it works out that it's almost exactly the same as the actual game when you're talking about unit timings and stuff. So that is one small abstraction, but it makes the computation way faster in not having to actually go and simulate the gathering of every mineral. So some questions. Can this generate build orders for lowest possible time to build any unit? Or do I always have to put in an arbitrary build order? So this user interface right now, in its current form, just lets you draw build orders. Okay, so it runs the build order that you put in through its visualization system. It simulates the build order and then draws it for you. The search system that I have completed, it will, if you give it... well, actually, if I go to my website, why don't I just do this? Research or publications, build order optimization in StarCraft. Here's the paper. So this is the paper about this search system and what it can do. And if you go to my website here, there's another one. In this paper, what I did was I made an algorithm which, instead of saying, I want to get to 12 Marines as fast as possible, what I did was say, get me as much army as I can in the next 5 minutes. And so that's what this build order did. This build order system did. So here's the paper for that. You can go like ! Website and read the publications if you want. But I don't want to spend too much time on this build order stuff because that's not really the point of the lecture, right? I'm actually going to be working on this on stream this week. Okay, so if you're more interested in that, tune in when I'm not lecturing, and I'll be working on this on the stream. Yes, I am going. Someone else asked, "Am I going to be showing off assignment 3 submissions?" I am going to be doing that as well today. Actually, let me do that on Thursday. Okay, so I apologize that I'm not going to be showing that off. Today was about assignment 5 in StarCraft AI. I will 100% do that on Thursday. I have all the submissions, but I haven't sorted them yet. So apologies for that. I will be doing it on Thursday for anyone who is tuning in just for the assignment 3 cool stuff. Thursday, I promise you. I promise you. Next lecture. So if you're watching this on YouTube, go to the next lecture if that's what you're looking for. Okay, but that's the build order stuff. I just wanted to show that system off and show you that you can play with it because it will actually help you for the project, right? Okay. So what algorithm did I use to actually plan these build orders? Well, oh geez, I'm not actually, okay. What I did was an algorithm called a depth-first branch and bound algorithm. So which with any search algorithm, what you're trying to do is you're trying to minimize some function, right? And so the function that I was trying to minimize was the amount of time it takes to build to the goal that you gave it. And so the system had low memory usage. It was any time, meaning that, so remember how we had an algorithm like A star? So the A star search algorithm, you run it to completion, and when it completes, you get the solution. But you cannot trust any solution. There's no solution in A star until the whole algorithm is done. With this algorithm, and I'll show you how this works, it's called anytime, meaning that there will be gradually improving solutions over time that you can save and load the search actually between frames of computation in order to get gradually better solutions. Now, there will be a best solution, and you can wait for that best solution, or you can cut it short if you want to. We can also use like upper and lower bound heuristics. So this is a really cool thing, is that if I go back quickly to this screen, So remember when we did heuristics for our search algorithms? Well, let's think about this. If I want to build a Dark Templar, right? So when we did A star search, our heuristic guess at how long we have to go to the goal was like the Manhattan distance. Remember that? So we had to have a guess at how far we still have to go before we reach our goal. When we're talking about how far in terms of distance, then we're going to use a distance formula like, okay, I still have to go at least 100 units of time. I have to go at least 100 distance to get to my goal. That was our admissible heuristic when we talked about the A star search algorithm. What would an admissible heuristic be for build orders, right? So we still want an admissible heuristic. What could it possibly be? Well, if we look, think about it this way. Let's say I'm at the point where I've just built my first pylon. So I'm over here in this build order. And I want to say, how much time will it be, at the very least, before I get to Dark Templars? Okay? Well, one of the heuristics is called a landmark heuristic. It's called a landmark heuristic because there are a number of different landmarks that I have to reach in sequence before I can build a Dark Templar. So, what I can do is, well, I don't have a gateway started yet. So if I know I'm going to have a gateway. After that, I have to have a cybernetics core. After that, I have to have a citadel. After that, I have to have a Templar archives. And only then can I even begin to worry about Dark Templar. So my heuristic for the build order search was, well, we can take the build time of a gateway, add the build time of all these buildings that have to be built in sequence down the tech tree, and that is like our distance heuristic. So that landmark heuristic in build order search is like the Manhattan distance heuristic in A star search. So all of those things that you learned for other more simple pathfinding algorithms can be applied to more complex versions of the search as well. So I just wanted to go over that because it's kind of cool how, while it may not seem obvious at first how you could make a heuristic like this, but you can. So let's go back over to the PowerPoint. Okie doke. So what does that actually look like when we're talking about build orders? Well, here is a search tree for build orders. So if I look up at here, what I've done is I've started by building a probe. All right. So I've started by doing that like probe, whatever. And I'm at a current state of the game. From every state of the game, there are a certain number of actions that are actually legal for me to build, right? So at the very start of the game, if I just have like one pylon, the things that I can build legally are another pylon, a probe, and a gateway. That's like all I can build. I can't build a cybernetics core yet because I don't have a gateway yet, right? I can't build a dragoon yet because I don't have a cybernetics core yet. And so just like up, down, left, and right, and maybe I can't go to the right is not a legal action, then cybernetics core might not be a legal action. So we can use the same type of search algorithms to do this sort of thing. So what we have here is a build order tree with increasingly good solutions going from left to right. So we're going to run the build order planner, and at some point it's going to find a solution. So it's a depth first search, and it's called branch and bound. So what I can do now, branching means that we go like, in a tree search, depth first. The bounding part is the really interesting part. So if I find a solution, so here, for example, one possible build order is probe, pylon, gateway, cybernetics core, assimilator, dragoon, probe, pylon, dragoon. Oh, by the way, this is a build order to get to 2 dragoons. So now that took 5,397 frames. That is a new lower bound on the amount of time it takes you to get to 2 dragoons. So any solution in the rest of my search that goes longer than 5,397 frames will be a worse solution. So what I can do is say, okay, from this time in the search, I'm going to add my heuristic, my landmark heuristic, and if that value is greater than my current bound of 5,397, I'm going to throw it out. I'm never going to search down that tree. And that's the process of like pruning your search tree by throwing away actions that will lead you to suboptimal results. So left to right here, what I've done is I've plotted every new better build order that I get. So the build orders that I see from left to right as I search longer and longer are of increasing quality, right? So it goes 5040, 4800, 4700, 4600. So this means that like by the time I've gotten to here, if I let it search for a few more seconds, I've gotten a build order that might be minutes shorter. And so yes, I want to let the search go for a certain amount of time until the search finishes, and I would get to the best possible solution. And if you look here, the quickest way to get to 2 Dragoons is by going probe, gateway, gateway, assimilator, cybernetics core, probe, Dragoon, Dragoon. Right? That's the fastest possible way of getting to 2 Dragoons in StarCraft. So it worked. However, let's say that the best possible solution took 10 seconds to do the search for. Well, if I only have 5 seconds, then what I can do is at any point in the search, I can stop and just use the best solution that I've found so far. I don't need to wait for it to finish like I did with A-Star or something like that. So it's really cool that you can do this sort of thing like in actual video games and do build order search, etc. Now, other people have done the same sort of research where they used a genetic algorithm, right? So in 3200, we looked at a genetic algorithm, which was like a sequence, like we had a genotype and a phenotype. So the genotype is the representation, just a bunch of integers. And so if you go left to right as integers associated with build order items or with units in the game, then you can use a genetic algorithm where the fitness function is the amount of time it took to build something. So there's all sorts of cool like research that you can do in these areas. So what we did was we compared the build orders that the search system produced with pro-human replays, and all our build orders were faster than theirs. But, you know, that's not really a fair comparison because they were being attacked and stuff, but it's the only real comparison that we could make. And I got some other stuff here, but I don't want to go into those details too much. So what was the impact of that research? So it was implemented into UAlbertabot, the boss solution, and someone out there asked a question, said, you may have already found the best solution early on too. Yes, but we don't know that until the search stops. So we either stop at a given time limit or when the search has exhausted all possible avenues, right? So let's say that the search will complete in 3 seconds, but our time limit is 5. We don't arbitrarily wait the 5 seconds, right? We stop it when the search says, I have nothing left to search, or when our time limit is hit, whichever comes first. So another person asked if this could be done in real time. Well, yes, all of the build orders of UAlbertabot are planned in real time by this system. And so in UAlbertabot, the way it works is that you say, I want these counts of units, and then it will run the build order search, and it runs in real time with no timeouts. And the first year that this was implemented, UAlbertabot came second place in the competition, and so it was tested in a real tournament environment, and it is real time. However, when I say something, I've given 2 conflicting pieces of information right now. The first piece of information was that BWAPI is a blocking system, meaning that, let's say, for example, that I wanted to give my build order planning system 5 seconds to do its search. Well, that would mean that when I run my search, the game is going to be paused for 5 seconds. But in the tournament, you can't take 5 seconds of computation for 1 frame. You have 50 milliseconds to do all your computations for 1 frame. So what I did was this search can be paused and resumed. Okay? So inside UAlbertabot, what happens is you start a search, you do everything else, like all the micro, all the building placement, everything else in the bot happens, and then it says, okay, how long did all that stuff take on that frame? I'm going to take 50 milliseconds, subtract the amount of time that I used on other systems, and use the remaining time within that 50 milliseconds to go toward the search. So it searched for maybe that, let's say 40 milliseconds on that frame, paused the search, then it goes to the next frame of the game, and then it resumes the search for however much time it has on that frame, and it does that for 5 seconds worth of game time. And so that's how you're able to do something like that. Now, you may ask, why didn't you just put it in another thread? I am a terrible multi-threaded programmer. So yes, you could have just put the search in another thread and then waited for the result. That's a much easier solution probably. Okay. The second problem that I worked on was algorithms for combat in the game. So part of the real challenge of combat is that you have a real-time system, so it's got to be fast. You've got to somehow do state evaluation, right? So in the build order planning system, the state evaluation was difficult because, in the build order planning, the state evaluation was easy. It's just how long did it take, right? You look at a potential solution, and you say, what is the current frame of the game? How long did it take to build that? In combat, it's not so easy. And also you have multi-unit control, which leads to a bunch of problems. So we have very little time to decide on a move, and we don't have access to the source code. Well, you could say, well, maybe you could launch an instance of StarCraft and run the simulation, and maybe that's a possible solution. But with StarCraft, we can only run the game at 64 times speed. You can't save or load the game states, which you need in order to do something like an alpha beta search. So again, I had to write my own simulator. So like half of my PhD, I probably spent like 3 years just writing simulators. But it was fun. I really liked writing simulators. So I wrote something called SparCraft, right? You got to be clever with your names. And so the units are sparring, it's SparCraft. Get it? Haha. Okay, so this was a system that I wrote that did very basic unit combat. So units could move. They had the properties of the units in the game. They dealt the same damage. They dealt the same... They had the same armor, like all those properties were imported from the game. However, I did cut some corners in terms of like there were no unit collisions. Okay, so it doesn't do everything perfectly, but for the basic simulation of movement and combat in StarCraft, it did a good job. So that was the simulator that I wrote. Now, how are you going to actually do state evaluation? So remember back to 3200. Now we're talking about assignment 3 from 3200, which is the Connect 4. Remember Connect 4? So we had to do Minimax. So I'm going to try and do Minimax in StarCraft, right? So let's do Minimax in StarCraft. How crazy would that be? Well, I've got my simulator. I can have states, but now I have to actually write the search algorithm. And part of the search algorithm is when you come to a non-terminal state, you have to be able to evaluate that state somehow. So, well, if you're at a terminal state, remember in Connect 4, if you're at the end of a game, you can just say win or loss, 1 or 0, really easy. But of course, our search algorithm can't always search to the end of the game, so we've got to be able to somehow evaluate the intermediary nodes in that search. And so that's a really difficult problem. So let's just look at that. What we did at first is sort of like what they do in chess, okay? So when you write your first alpha beta system for chess, what you're going to do is write some sort of formula-based evaluation. So let's say pawns are worth 1 point, queens are worth 9 points, rooks are worth 5 points. We're going to sum up all those points to see who is winning. But of course, you know, in a game like chess, yes, it's better to have more pieces, but you might sacrifice your queen in order to get a checkmate next turn, right? So it's not a perfect system. And what we did was we did a formula-based evaluation, which worked okay, right? What we did was we added up, we had this formula based on the amount of damage a unit could do, the amount of hit points that it had remaining. But like a Dragoon versus a tank, that's a hard formula to come up with. And so we said, no, okay, we're not going to go with that. We did some experiments and they worked okay, but not well enough that we wanted to go forward with them. Another thing that people do in research, and especially in the area of Monte Carlo tree search, is they do random playouts. So, in the game of Go, for example, if you watch that AlphaGo movie, one of the ways that they evaluate the game in Monte Carlo tree search for Go is to say, okay, what this evaluation is supposed to do is say who is winning. Right? So who is winning from this game state? So you look at a state of the game, and if you're a professional commentator for a sports game, you might say, oh, this team is winning, or oh, that team is losing, or whatever. How do you know who's winning or losing? Well, the formula-based evaluation wasn't doing a good enough job. One thing researchers have tried is to say, well, if one person is ahead and one person is behind, if we do a random playout, meaning if we go to the end of the game with both people making random decisions, and we do that some number of times, then the person who was winning should win most of those games, right? So let's take a game of Go, for example. If you take a game of Go and you play out 100 games where people make random moves, and you find that one player won 80% of the time when both players took random moves, then it's probable that that player was winning at that state, right? They were ahead at that state. So we tried random playouts, but random playouts suck in real-time strategy games. And the reason is random actions literally means moving in any direction and attacking any unit. So we had units just running around the map, never actually fighting to the death. So we couldn't do random playouts because the games would never finish because there was one Dragoon up in the corner just dancing somewhere. So that didn't work out. What we decided on was we did a symmetric behavior playout. So what we did is we wrote some scripted behaviors, for example, like attacking closest, right? And then we said, okay, if both players just meet in the middle and attack the closest units, who wins? And so that was what we used for our evaluation, and it ended up working really, really well. So what is a scripted behavior? So a scripted behavior is like a simple strategy or a policy. It has a low computation cost. One possible example of a scripted behavior is just attack the closest unit, right? So you may implement this in your bot. I highly recommend implementing attack closest. It is the most effective, simplest solution that you can have in a StarCraft bot. So whenever you go to choose a unit target to attack, you attack the closest enemy unit to your own unit. Another script could be attack the thing with the lowest hit points. So here, for example, instead of attacking the closest thing, which is the tank, I could say, well, the thing with the lowest hit points is going to die first, so why not attack that first? So I could try and walk past the tank to attack the Marine, but maybe while I'm walking past it, my units get destroyed by the tank, right? So that's why anything other than attack closest is actually quite difficult to implement correctly. Or we could say run away, right? So what we did was we used these symmetric, meaning that both players are going to choose like attack closest or some other maybe more intelligent script and attack each other, and that was our state evaluation. So rather than trying to sum up the unit hit points or do random playouts, we did these sort of symmetric playouts, and that worked out really well. And then the multi-unit control problem was also an issue. So here's something that you have to realize when you're doing real-time strategy game research is that, let's say in a game like Go. So Go is a difficult game. There's like 300 possible moves you can make at any given time, right? But in StarCraft, your move at a frame of the game is to issue actions to every unit that you control. So one unit has a number of different actions that it can choose, but your player has to choose on an action for every given unit. So at any given time step, if you have U units, each of them having A actions, then the amount of different moves you have is exponential. It's actually A to the power of U. So if you have like up, down, left, right, and shoot, so that's 5 actions. If you have 50 units, then the number of possible actions that you choose from on that frame is 5 to the power of 50. It's crazy, right? So it's a way harder problem in terms of search to solve this than it is for something like Go. So also you have things like in traditional algorithms and traditional games like alpha beta search that we learned about in 3200. It's kind of easy because you have alternating moves and those moves have instantaneous actions. But in real-time strategy games, you're actually acting at the same time, and your actions have durations, right? So if you choose to shoot somebody, that takes a certain amount of time. It just doesn't instantly get implemented. So what we had to do was I had to modify existing algorithms. So I had alpha, beta, Monte Carlo tree search, and modify them so that they now took into place things like simultaneous moves and actions with durations. So what you end up seeing, unlike Minimax or alpha beta search, is that in StarCraft search, you can actually have like units acting multiple times in a row before the other unit gets to act. So for example here, let's say we have a Marine attacking nodes in blue. When the Marine attacks, its cooldown is longer than the Zergling. So if a Marine attacks, you may actually have the Zergling get in 2 or 3 actions before the Marine can act again. So, all right. Someone out there had a question. In StarCraft AI tournaments, is the AI limited to actions that a human could perform? No, it is not. So that is currently not a limitation. The reason it's not a limitation is that we decided that until AI systems start regularly beating humans, we will not restrict the amount of actions that they can do. However, the Alpha Star system that Google made did place a restriction on APM. So Alpha Star is superhuman in the fact that it can issue 2 different commands on the same frame, but it cannot issue more actions per minute than a human could issue, right? It limited to like 300 or something like that, or 180, I can't remember. However, Alpha Star and all other AI systems also have a superhuman quality in that they have perfect precision, right? So that means that if I want my unit to attack another unit, I just call unit.attack enemy. And that is a perfect precision. I cannot misclick, right? So as much as DeepMind loves to say that their micromanagement is not superhuman, like it doesn't break any human rules, it does have infinite precision. And so it will never misclick. And so that is superhuman, right? So that's the answer to that question. So what I did in my research is that I came up with, I had to modify the alpha, beta, and Monte Carlo algorithms to consider duration. So I called it alpha, beta, considering durations, or ABCD. I wanted it to have, again, if you ever go into research or you ever release a GitHub project or you ever make an algorithm, name it something clever. Because there were so many people who cited my papers because it was called ABCD and they remembered it. I was told by dozens of people that they only remembered my paper because it was called ABCD. But if I called it something other like, Dave's algorithm, they probably wouldn't have remembered it. So unfortunately, the naming of your projects and the naming of your research, the branding of it really matters. So try and be as clever as possible when you're naming your projects. So the search algorithm beat all the scripted players. It was really good. And the UCT is a flavor of Monte Carlo tree search, and it outperformed ABCD. I won't get into this. Oh, I also did something else called portfolio greedy search. So one of the issues with the StarCraft search is that we do have this exponential branching factor. Remember how I talked about the unit depth, right? So this means that even good search algorithms can't sometimes escape depth 1. If we have 5 to the power of 50 as our branching factor, we're going to stay at that first depth. We're never going to go to the second step, right? So how can we solve that problem? Well, I came up with another algorithm called portfolio greedy search. This was a greedy hill climbing algorithm that actually did a better job than the search algorithms. And here's how this worked, if you're interested. So what I did was I created a script portfolio. So how I talked before about like attack closest, attack weakest, attack lowest hit points, run away, gather, what else? Attack the highest DPS unit. There were all these different scripts that I wrote that are often used in real-time strategy games. So the first step in this algorithm, PGS, is that it takes in a portfolio of functions, and those functions guide your units. They're scripted solutions. Then it takes in a game state, like this is the current game state that I want to make an action on, and the output of this function is the move that you want to perform. So what it ended up doing was it's a greedy hill climbing algorithm that instead of deciding on individual actions for each unit, it iterates over possible assignments of scripted actions to each unit. And so what it will do is we have like Dragoon, Zealot, Zealot, Dragoon. It will create assignments from scripted actions to each unit, and then it will evaluate that with, again, it does a simulation, and then it will decide on what the best assignment of those scripted actions to the units, which the best assignment is. And what we found was that it did way better than the search algorithm the bigger the combat size got. So, for example, if we ran the portfolio greedy search against the alpha beta considering durations algorithm on battles of size 8 versus 8, well, when you only have 8 units, that exponential branching factor isn't so bad, right? We can look over all the possible actions for 8 units, no problem. So alpha beta for small unit sizes, for small battle sizes, did better than portfolio greedy search. But as soon as you start getting into battles of size like 16, 32, 64, that kind of thing, portfolio greedy search blows it out of the water, right? Even though it may be missing some of the optimal actions, the way it does this greedy hill climbing solution is way better when it comes to larger battle sizes where your search algorithms just don't have a chance, right? So that's kind of where I left the battle stuff. So again, if any of this stuff appeals to you and you were really considering doing like a master's degree or something like that, all of these research avenues are still open, and I would be happy to work on this stuff with people. However, okay, so what we've shown is that StarCraft as an AI environment has a huge state and action space. It has real-time decision-making. It has properties similar to real-world problems. So we couldn't possibly just apply more CPU. We can't wait for Moore's Law to solve this problem. We need new algorithmic solutions. We have human experts that can evaluate agents. We have lots of public interest and excitement. It's a huge educational tool and a student motivator. So I think that, like, on the whole, StarCraft AI is just a super great environment to do. StarCraft is a great environment to do AI research in. And I think, okay, I had to skip forward a little bit because I had some extraneous slides. So the last thing I wanted to mention was how sort of UAlberta the bot that I made, incorporated this. So UAlberta it was written by me and some other people, the initial version, back in like 2010. In 2012, I completely rewrote it from scratch because it was garbage, and released it as an open source project. So it's here if you want to go look at it. It plays any of the 3 StarCraft races. It won the competition in 2013, so I get to say I was a world champion at some point. Now it doesn't perform anywhere near as well as the more modern bots, but I actually have a job now, so I can't spend a lot of time updating it. But it has a hierarchical decision structure. So I think this was a cool way of doing things. The initial version of UAlberta had all these modules, and it still does. So it has like a game commander, it has a combat commander. So like the game commander makes these really high-level decisions. It tells the combat commander to accomplish a specific task. The combat commander has squads. The squads give out the micro assignments. So it's almost like a military command structure, right? Like the game commander doesn't need to know how the micro is being done. That's the squad's problem. It manages the workers. It manages the production. There's some build order stuff. And so initially, all of this, the whole bot was like hand-coded rules. If this, do this. If this, do this. The first thing I did was the build order search. So I replaced the hand-coded build orders that were initially in the bot with the build order search system. Then all this
combat stuff, all these formulas and guesses and hand codings of attack timings and stuff that were in the bot, I replaced with the StarCraft simulator. And then the strategy manager, that was replaced with the UCB1 algorithm for deciding on strategies. So what I did was, over the course of my PhD, I started out with this completely rule-based solution that was kind of dumb, and then took these individual modules and replaced them with more intelligent AI-based systems. And that apparently, it worked pretty well, because a lot of people ended up building on UAlberta-bot. And so I have this like family tree of bots that have been built since then. And like, I think something like between 20 and 30 bots over the years have been based on the source code, the 2012 version of UAlberta-bot. So it really goes to show that if you spend time, like, here's a really underappreciated part of research, okay? Is that I, as a professor, I am evaluated by my research in terms of like getting promotions, getting more money, all that kind of stuff, based on publications, okay? So now this is a bit of a salty point for me, so I apologize if I feel like I'm ranting. But so if I submit to better conferences, my research looks better, right? If I submit to better journals, my research looks better. For me personally, I have been a part of this StarCraft AI community as part of these smaller conferences my entire research career. And so what I want to do is build up those smaller conferences. So I've been submitting publications to smaller conferences, and so the work doesn't look as good from the terms of the university, because I'm not submitting to like Nature or whatever. Not to say I would get into Nature. My publications aren't that great. But like, it's kind of a double-edged sword. You want something to grow, so you submit there, but personally it's a detriment because you don't have these like high impact factor journals and stuff. The second part of that is that, like I said, I spent like 3 years of my PhD writing simulators and writing code and writing bots and releasing them on GitHub. And if you go to GitHub, like, I don't like humble bragging, but like hundreds of people have used UAlberta-bot for their research. There are lots of citations out there of people who were able to take my bot and like modify it and do their research. And so one thing that's never considered is like not only your own publications, but how much other work have you been able to enable because of the work that you've done, right? So I'm a huge proponent of releasing your research code as open source projects, spending time writing documentation, writing instructions, releasing YouTube videos and tutorials to get other people excited, to get other people involved in this. And there's a huge opportunity out there for everyone, including you, including students, to write your own bots, to release it as open source code. And I will tell you that as a career decision, nothing was better for me, way better than any of my publications and way better than any of my teaching, was the running of the competition and the implementation of like open source projects, because way more people know me for that public facing work that I've done than like the private research that only a couple of people care about. So the whole point of that was to tell you that even though it may not help your academic career, it helps a lot of other people, which in my opinion is the whole point of education and academia, is to help foster research, right? So it may not help your own publication count, but it does help the global publication count, which is, in my opinion, what research should be about. All right. And oh yeah, I also wrote another bot for StarCraft 2, and I have some slides there, but I don't really need to talk about that because this course isn't doing StarCraft 2. But yeah, that is pretty much it for this class, and I hope I've convinced you that StarCraft is a great environment for AI. Someone had a question. They don't look at citations. Oh, so I apologize. They do look at citations. So if someone has written a publication and cited my work, that obviously does a good thing for me, right? So that like helps my H-index, and they look at the H-index and they say, oh, people are using their work, therefore their research is better. However, by far the main thing that they look for, they being like university administration, is the impact factor of the conferences and journals that you get submitted to. It's annoying, However, I'm sure that if you had like a 100 H factor, well, the H factor in itself, okay, I should explain this to the students who are not familiar with H factor. The H index of a researcher, if you have 6 papers that each have 6 or more citations, you have an H index of 6. And so it's just like the higher someone's H factor, the quadratically better they are as a researcher, or in terms of getting citations. So I think mine is like 11 or 12 or something like that, meaning that I have at least 12 publications with 12 citations each. And so that's just like, it's a crude measure of that. However, what that doesn't show is that like 400 people have downloaded my bot and used it, as a basis for their bot, because those people don't necessarily write publications, but they are using it for like hobby research or advancing the state of the art in AI. So that's the end of my rant. It's just annoying when you're at this stage of your academic career, you have to make real decisions about like, do I do this for my own gain or do I do it for public gain? And those two things, unfortunately, are not always viewed as the same thing from the point of view of the academic world. Okay, so next class, I promise you, we will be showing off assignment 3 solutions in depth. That may be the only thing that we do in the next class. How about that? Just to make it up to you. So that's it for today's lecture. I'll see you on Thursday.